Welcome to the Explainer. Today we're diving into a really powerful image processing technique called adaptive thresholding. Look, if you've ever tried to segment an image with uneven lighting, you know exactly how frustrating it can get. Well, this is the tool designed to solve that very problem.
So let's start with a classic problem. On the left, you've got a chest x-ray, and you can see right away the lighting is all over the place. It's way brighter on one side. Now on the right, that's what happens when we use a standard global method, in this case, Otsu's thresholding. Because it's trying to find just one single brightness cutoff for the entire image, well, you can see the result. It's a complete mess.
And this really begs the question, right? Why did a tool that usually works pretty well just completely fall apart here? The whole left side is just blown out with white pixels, and the right is almost totally black. So what went wrong?
Well, this gets to the very heart of what we call the global problem. We're in a situation where applying one single rule across the whole image just isn't going to cut it.
You see, a global method like Otsu's calculates one single brightness value and then uses that number for every single pixel. When the lighting is uneven, that's a huge problem, and this happens all the time in the real world, especially in medical imaging. MRIs can have this thing called a bias field, which is just a fancy way of saying there's a slow, gradual change in brightness across the scan. In cases like that, a one-size-fits-all approach is pretty much doomed from the start.
So the solution is to get a little bit smarter about it. We need an approach that stops thinking globally and starts thinking locally, adapting to the conditions in each little part of the image.
And that, right there, is where adaptive thresholding comes in. Instead of one threshold for the whole image, it calculates a unique, custom threshold for every single pixel, based on what's going on in its immediate neighborhood. Think of it this way. Instead of one speed limit for an entire city, you have a different speed limit for every single block.
This slide just nails the difference perfectly. On the left, global thresholding, one rigid rule for everything. On the right, adaptive thresholding, a flexible, local rule for each tiny part of the image. That is the key insight that's going to solve our problem.
Okay, theory's great, but let's see how this works in practice. The first major decision you have to make is defining the size of that local neighborhood, and we call that the block size. And as you're about to see, this choice can totally change your final result.
So yeah, what's the right size for this neighborhood? Should it be small, focused on the tiny details? Or should it be large, to get a sense of the bigger picture? Let's find out. Here you can see the results for 3 different block sizes. We've got a small one at 11 pixels, a medium one at 31, and a large one at 61. Now notice how the smallest one, on the left, it captures really fine detail, but it also introduces a ton of that salt and pepper noise. As you make the block size bigger, the result gets way smoother. There's definitely a trade-off here. So here's the deal with that trade-off. A small block size like 11 is super sensitive. It's great for fine textures, but you get a lot of noise. A really large block size like 61 gives you much smoother boundaries, but it starts to act a little bit like a global threshold again. For things like segmenting organs, which have pretty smooth edges, a medium to large block size is often the sweet spot.
Okay, so we've picked our neighborhood size. The next step in our toolkit is deciding how to calculate the threshold inside that block. And there are 2 really common ways to do this. Here, we can see them compared side by side. The first one is the mean method, which is super simple. It just takes the average of all the pixel values in the neighborhood. The second is the Gaussian method. This one's a little more clever. It uses a weighted average, so it gives more importance to the pixels that are closer to the center of the block.
And Gaussian is often the one people prefer. By giving more weight to those central pixels, it just tends to produce smoother, cleaner boundaries with less noise. This weighted approach also does a better job of reflecting how illumination actually changes in the real world. It better models the physics of light, which is especially useful in medical scans.
We are almost there. We have a block size and we have a calculation method. There's just one last little parameter we can use to really fine-tune our results, a simple value called the constant C.
So what is C? It's actually really simple. It's just a constant that we subtract from the calculated threshold for each pixel. The best way to think about it is like a manual tuning knob that lets you make the final result just a little bit stricter or maybe a little more lenient across the whole image.
And you can see the effect plain as day right here. We're looking at results with C set to 0, 2, 5, and 10. Now watch what happens as we increase C, moving from left to right. See how the amount of white, the foreground pixels, just starts to shrink? We're effectively making the threshold stricter and stricter with each step.
So the key takeaway is this. Increasing C gives you direct manual control to make that threshold stricter, which means you end up with fewer foreground pixels. It's the final lever you get to pull to get your segmentation looking just right.
So let's put this all together. By choosing a block size, a calculation method, and a value for C, we've basically assembled a complete and super powerful adaptive thresholding toolkit.
And this slide just illustrates our journey perfectly. On the far left, you've got the original image with that really tricky lighting. In the middle, the total failure of the global Otsu method. And on the right, our successful result using a fine-tuned adaptive Gaussian method. The difference, as you can see, it's night and day.
And here's a quick summary of everything we just built. We saw why global thresholding can totally fail, especially with problems like MRI bias fields. Then we saw how adaptive thresholding is the perfect solution using a local threshold for each pixel. And finally, we learned how to tune that block size and the C constant to get exactly the result we need.
This leaves us with a final thought. Now that you've seen how this powerful technique works and how you can tune it, where in your own projects might you now choose to use adaptive thresholding instead of a simpler global method? It is a really powerful tool to have in your toolkit.